All right. Thank you, Jamie. So my talk is on application of machine learning to post-earthquake damage assessment of building structures. I'm going to keep it at a fairly high level. So I'm going to focus on the frameworks we adopted, sort of the context in which we adopted machine learning, and then some of the challenges. So trying to build on that hope or hype theme that we started with. Is there any there kind of thing? So these are so I'm going to talk about two main topics. Both are related to post-earthquake damage assessment of buildings. One focuses on individual buildings, another on portfolios, and then I'll end with some challenges. So yesterday, Ellen mentioned that a lot of these AI methods have been around for decades. Well, it turns out that within the civil engineering community, we've actually been exploring these various methods for a long time as well. So as early as the late 90s. Actually, the fourth paper on that list is actually a state-of-the-art review, right? And this is on application of machine learning in civil engineering, and this is in 1997. So that gives you some perspective as to the amount of work that was actually going on between the late 80s up until the mid to late 90s. So starting with individual buildings, so I thought I'd start with the talking about the state of the art for post-earthquake assessment of individual buildings, and Shirley alluded to some of this, the overall process. So obviously we're familiar. So there's in-person inspections, right? And to take a step back, I'm going to talk about portfolio-based assessment in a second. So here we're talking about individual buildings. So think you're a building owner. You have maybe a building that that is of particular interest to you, maybe a small cluster of buildings. And so you might hire engineers, have engineers on staff ready to go inspect buildings after an earthquake, right? So we're talking about individual in that context, right? So they're in-person inspections. So the inspector would go, they would observe damage, they would document it. You may or may not have information on response measurements from instrumentation. And then the inspector has to make a decision about the safety state of the building. And that's based on what he or she sees, and if they have any information on measured response, as well as their engineering judgment, right? And there's nothing wrong with that. I think in terms of engineering judgment, I think that's something that we need to have part of the process. So the challenge is, can we do some pre-event response and damage simulation, couple that with what we call virtual inspection and machine learning, to one, get rapid preliminary assessments of the safety state. So again, going back to, let's say you're an owner with a small cluster of buildings, maybe you want to use these assessments to help prioritize which buildings should have in-person inspections, sort of how that should be sequenced, and then also to augment the in-person assessments, right? So basically we create some type of companion, some type of recommender that can actually help inform the decision of the person doing the field inspection. So with this slide is gonna get pretty busy, so I'm gonna start with the end. And so basically what we're trying to do is we're trying to develop some type of statistical learning model that links either response demands and or observed damage with some measure of the reduction in the overall capacity of the building, right? So one of the big challenges with in-person inspections is, as an inspector, you'd go around, you would observe damage in different places, and it's very hard to sort of get a quantitative sense of how that damage is reflected in terms of the residual capacity of the structure. So we're using machine learning to make that link between responses that you can measure, things that you can see, and the impact on residual capacity. So the first step is getting some sense of the performance of the intact structure, meaning the undamaged structure, right? And so you can use some type of analysis to measure the structural capacity of the intact structure. And in this case, we're using collapse performance as the metric, and the level of reduction in collapse safety as the measure of residual capacity. So the next step is to use what I'm calling sequential nonlinear response history analysis to get us. So basically what you're doing is you're using simulations to damage the building and then get a sense of the structural capacity of the damaged building, right? And again, you're using sequential nonlinear response history analysis. You have a first ground motion that's going to damage the structure, and a second set of ground motions that's going to assess the performance of the damaged structure. Right, and using those two pieces of information, you can get a sense of the residual capacity of the damaged structure, right? And that residual capacity, that's like our response variable, right? That's the thing that we're trying to get. That's the thing that we're trying to predict. As you'll see later, we pose two types of problem. One is a classification problem, one is a regression problem, and you'll see how those two things differ in a sec. And so the next step is now you want the features, right? So you want to get a sense of, during the damaging event, what level of responses and or what level of damage do you have? So these are going to be your features that are going to be built into the statistical model. So I'm going to show two more slides that basically have this same framework. They're going to sort of be color coded and a little bit busy, but just keep this framework in mind. This is the framework that we utilize for the next couple cases I'm going to show. So for the first case, we tested this on a pretty small building. So this is a 4-story concrete moment frame building. And for this particular case, we used Randam forest, which is a we used it specifically for classification, right? So again, so this is the same framework. It's color coded. So if you look at the green, part of the flow chart, that's where we were assessing the performance of the intact structure. And again, we're using collapse performance. So we evaluate the collapse safety of the intact building and we get some measure of the collapse statistics. The red part is where we quantify the performance of the damaged structure. And the yellow part is where we get information on the responses and damage under the damaging event, right? And all of that feeds into this bar where, again, I mentioned this, in this particular application, we set this up as a classification problem. So basically what we're doing is if the collapse capacity of the damaged building is reduced below a certain threshold relative to the intact building, we're saying the building is not safe, right? And that's obviously, that you can think of that as a policy decision because it's deciding, okay, how much reduction in safety are you willing to live with? And then if it's above or below, we say safe or not safe based on that. And again, so we're using Randam forest to do this particular classification. Randam forest, not to get too much into the details, but it's part of a broad class of algorithms, so-called tree-based algorithms. I like it because it's pretty intuitive and it's relatively interpretable, at least if you understand how the algorithm works. So the basic idea is you set up this algorithm and then earthquake happened, building gets damaged. You might have some response measurements, or you may have that in combination with observed damage. You may only have the observed damage, but the idea here is that you can use this predictive model to classify the safety state of the building, right? And again, the idea here is that you're using this either for preliminary assessments to guide where you're going to send your inspectors, or as to augment the in-person inspection, meaning you have someone in the field observing and has to make a decision, and it has this additional piece of information that they can use to aid in that decision making. So we also applied the framework to a tall building. So this is one of the, for those of you that are familiar, the building, one of the buildings that was used as part of the PEER Tall Building Initiative project. So it's a 42-story reinforced concrete building with a dual system. So it has a concrete core and a moment frame. And again, a similar framework. There are some things we had to do different here because of the fact that it was a tall building. So again, so the green part again is where we assess the performance of the intact structure. I should mention in this case, we set this one up as a regression problem, meaning instead of trying to classify the safety state of the building, we're just trying to quantify how much the intact capacity is reduced, right? And that's what that this kappa represents, right? So some measure of how much the capacity is reduced. So again, the green is where we evaluate the performance of the intact building. The lower part of the yellow is where we evaluate the performance of the damaged building. That feeds into what we're calling a residual structural capacity index. Again, that's our response variable. And then the upper part of, you see where it says EDP patterns. So again, this is a tall building, so it obviously has a large number of components. not all of them are going to be impacted by the shaking. And so trying to be strategic about which of these response demands or which of these damage conditions we actually want to incorporate in our algorithm. So the first thing we did is we used something called dispersion filtering. So for those of you that are familiar with nonlinear response history analyses, you know that under larger demands where the response gets to be more inelastic, the dispersions are generally higher. So basically what we said is, if the dispersion is below a certain threshold, we're just going to filter that out because we know that the demands are likely to be pretty low. And then we used a technique called lasso, which does feature selection by shrinking certain features. So again, we were able to reduce the number of features that are incorporated into the model. And the idea here again is, if this is a tall building, if you're relying on inspections, you want to be strategic about where you need to go and do inspections, right? So you don't want to include all of the features, all of the responses and damaged components as part of the features, right? So we use lasso for feature selection, and ultimately we use support vector machines to develop the predictive model. Okay, so just some practical considerations for this particular study. Again, I mentioned part of the idea is that these methods can augment in-person inspections. So you'd need to have some type of user-friendly interactive platform to be able to use it. You need buy-in from the structural engineer practitioner community, right? So I actually practiced for 6 years. So I understand the skepticism that's sort of ingrained in the community in terms of adopting some of these algorithms that, at least to some, seem like black boxes. And then obviously, you need a lot more broader studies in considering different types of buildings and algorithms and things like that. And there is some computational expense that goes into setting up this algorithm, right? So you need to do all of the pre-analyses and things like that to be able to set up your model. Okay, so now I'm going to switch to still with the theme of post-earthquake damage assessment, but now for building portfolios. And again, starting with the general workflow, same as with in-person buildings, but typically what happens after a major event is that the building department would commandeer a set of volunteers that would go out and do inspections, and they would tag the buildings red, yellow, or green. Red is unsafe, green is it's safe to go in, yellow maybe it needs some more inspections. And this process can take quite a bit of time depending on the event, on the order of weeks, even to months. So the challenge is, can we use predictive machine learning to do rapid preliminary damage assessments? And you can use this to do things like inform early recovery planning. You can aid in emergency response, right? So help early responders know where to go to look for highly impacted areas. You can do rapid assessments of economic loss, and you can also prioritize inspections, right? So this time it's prioritizing where you send teams of inspectors. So for this study, we used a data set from the 2014 Napa earthquake. This is just a summary of the earthquake. It was a moderate earthquake, 6.0 in magnitude. There's some information here. Roughly about 3,400 buildings or so were damaged that were considered moderately to severely damaged, and the losses estimated to range from anywhere from, that should be 500 million, not 50 million. 500 million to $1 billion. So the data set we have, it's a small data set, especially relative to the 800,000 or so that was discussed yesterday. And there's some challenges associated with that I'll talk about in a little bit. But this is the data set and the distribution in terms of the tags. Again, the distribution is skewed, which is, we actually expect that, or we hope, right? We hope to have a small number of red tag buildings, but in terms of applying these techniques, there are challenges associated with these skewed distributions. So we developed 3 different types of models. One where we used characteristics of the earthquake, the response, and the building. A second where we actually used damage descriptions. A third where we used images. I'm not going to talk about the images one because we didn't develop such a good model for that. We didn't have a lot of images. So starting with the one where we used features related to the earthquake shaking and the building. So the features are related to shaking intensity, how far you are from the epicenter, site parameters such as BS30. We evaluated several different algorithms. Random forest turned out to perform the best. And the age of the building, the shape, the intensity measure, and the bore joiner distance turned out to be the strongest features. We got about 66% accuracy overall, so not great. A big challenge was, and this is for the testing set, by the way, so we did the typical training testing split. A big challenge was because of the relatively small percentage of red tag buildings, we had a hard time predicting the red tag buildings. The thing that wasn't, that we weren't too concerned about is that a lot of the red tag buildings were predicted as yellow. So, you know, so yellow basically says, okay, you need to take a second look at that building. If we were getting a lot of red tags predicted at green, then we'd be a lot more concerned. The second study, we actually took the written descriptions of damage that was documented by the field inspectors, and we were able to train a model called a long short-term memory deep learning algorithm. So this is one of those algorithms that's able to predict sequences of things. So like the thing that finishes your sentences or your thoughts when you're sending text messages. We were able to get a lot better performance from this one, 86%. But then the thing we had to acknowledge, and we did, and we have a paper on this, was that we actually, if you think about it, we're trying to create a rapid assessment framework to sort of get information before the in-person inspection, but we're actually using the descriptions from that traditional process, right? So at best, you would say, well, we showed some potential here, but it actually raised a much more interesting question, which is, can you get as good a performing model from non-expert descriptions, right? And so that led me to think about that a little bit, and I'm actually in the process of a collaboration with someone in our psychology department to put, again, non-experts in a virtual reality environment, show them damage, have them describe things, and see if we can get as good a performing model from those descriptions. And if we don't, the next step is to think about, okay, are there things we can do, for example, create simple lexicons that they can use instead of doing the description from scratch, maybe put some keywords in there that they can select from to help basically target those descriptions. Again, some practical considerations. I'm going to skip over that. These are some overall challenges that we had based on our experiences. In the interest of time, a lot of them sort of came up in the discussions yesterday. In fact, I think all of them. So I'm not gonna dive into them. So there are a lot of contributors on this project. We received some National Science Foundation to do some of this work, and I'll just end here. I'll give a plug for some additional work that's going on within the earthquake engineering community. So for the structural engineers in the room, if you're attending the 2020 Structures Congress in April, there's actually 3 sessions that have machine learning theme sessions in them. One of them is I guess what they're calling an AI summit. So that's organized by the executive committee of SEI. And then there's a couple others organized by various committees. So if you're attending Structures Congress, definitely attend. And there's another session, for those of you attending the World Conference, I organized a session with Professor Bojar from ETH. Shirley is actually going to be presenting in that session as well. So if you're going to be in Sendai, definitely check that out. All right, thank you.